Nowadays, we mostly work with high-level abstractions. With all the tools and frameworks available to us, building software is so much easier today than it was in the past. Main challenges lie in finding the correct architecture and operationalizing everything from development to deployment and back. It's all about the lifecycle. And this is where MLOps comes in. In this video, I'll show you a minimal end-to-end ML architecture from data ingestion to model monitoring. You'll learn how to use MLflow to track metadata and artifacts from multiple models that we want to evaluate and compare, and eventually serve for inference. You'll learn 2 ways to deploy a model and what to look for once the model is in production, learning how to monitor drift, estimated performance, and user feedback. Let's get into it. So organizations are continuously trying to understand roles and responsibilities, and today we are going to look at ML engineering. So MLOps is a part of ML engineering. ML engineering is concerned with, among other tasks, model training and evaluation, and so is data science. So you could ask, why do you need a data scientist and a machine learning engineer? Just because the data scientist will be extremely focused on the model training, the features, the algorithms that you are using, and the data scientist has other types of responsibilities as well, from visualization and telling the story, while the ML engineer is focused on model training and evaluation from the point of view of operations. So it's not as relevant to the ML engineer whether the model is performing well or not, but rather that we can have access to that information so we can make decisions, and that works for the data science team as well as the product team. And so this was just to clarify something that I'm going to show next in this diagram. Don't be discouraged by the sheer size of this diagram. It's not that complex. So this Venn diagram that I showed here was just to clarify why data science is inside ML engineering here. There is just an overlap, and this particular responsibility of the data scientist was regarding the model. So this is why we designed this in this way. So let's go step by step, trying to understand what we are going to do here. So we are going to be working with some depression data, texts that are classified as depression or not depression. So there is a text and there is a label 1 or 0, where 1 is true for depression. So we have our data engineering pipeline, and you can check the video on DBT and DuckLake, where we explain in depth how this works, and we are constantly reusing this approach. And so we have our data sources. Currently these are the ones that are supported by DataLab, and DataLab is open source. If you want, you can fork it and change it and use it as you'd like. It's just a code base. There is no init command or anything like that. Just open it, check out the commands, add whatever you need. It should be fairly self-documented. So if you have any questions, also I'm on Discord, so feel free to jump in and ask me anything. And so we now support these data sources. The data sets we are going to ingest are from Hugging Face particularly, and so we have ETL, which includes ingestion, essentially downloading the data set into MinIO directly, and transformation, which means reading the data from MinIO using DuckLake and creating our final tables. These final tables will be a training set with an example ID, an input, a target, and a fold ID, because we are going to store the folds for cross-validation, so we can reproduce this across different algorithms using the same folds. And we also need a test set, which takes an example ID, an input, and a target, and this will be for logging inferences in another stage. So going to the ML engineering stage, we'll have our model, which we train using the training set as usual. During training, we will collect metadata that will log into MLflow. So for each training step, for each model that we are training, we'll create a run on MLflow. After starting this run, we can log metadata extremely freely. They call it tags. They also have a structure for input data and output data, but that's kind of over complex. Personally, I feel like tags were enough, and I'd rather have everything just available with one click. Anyway, you train your model, and in the end you'll have a serialized model, file, and this will be an artifact that you can log into MLflow. So in MLflow, you'll have the trained model that you can use for inference, and you'll have a bunch of information about how that model was trained, usually hyperparameters, evaluation metrics from the best split from your cross-validation, and evaluation metrics from your test set as well. These are the standard ones, and this is what you see here. We are going to log the evaluation metrics from the test set. We are just using accuracy and F1 for this. You can use ROC, AUC, which is probably even better than using F1. And so from these models, we'll pick one or several models, and we'll offer inference using a REST API. This REST API, we have a single endpoint that takes post requests or patch requests, and so when the user posts text or several texts into the inference API, it should return the label for each, and we do return the score, not the label. So the decision threshold is left to the user really, but this is just what we chose to do here. So the user will get the inference, but at the same time we are using Kafka as our queuing system or event log system. You can think of Kafka as a pub sub queue, but it's a lot more than that. It provides replayability. It is robust to disconnects and all that, because it's meant to be deployed as a distributed system, although we do not do that here because this is just a lab. And so we have two topics: one to get inference results. So once a user asks for an inference, a UUID will be assigned to that inference, a unique ID, and it will be returned to the user, and at the same time it will be published to the inference producer, or rather published using the inference producer. It will be sent to this topic over here, and it will be accumulated on the consumer until it reaches a given batch size, so we can drop this result into the lakehouse. Okay, and so the user will get that UUID. The user will be able to provide feedback on that inference. Once there is feedback, the user will request a patch to inference, and this will repeat something similar to the inference producer. So now we have a feedback producer which will update a given UUID with some feedback. So once our consumer or feedback or inference consumers reach a given batch size, they will be written to this table on our data lake. So this is DuckLake underneath, and for inferences we will be inserting. For batch updates, we will be updating each appending to the feedback, because this will be an array, a list of floats or double. Internally there is a queue. This will be emptied, and inference results will be received, filling up the queue and flushing to the lakehouse. And this kind of closes the loop. We can then use this information to compute several monitoring metrics, and I will talk about those next. those are not included in this diagram over here. This should give you, an overview on how to implement something like this. You could eventually, drop Kafka in favor of something simpler like gRPC or something like that, although it's not ideal because, gRPC is faster, but Kafka provides more robustness if you are going to do this in production. And if you have some bug, you can even replay one of these and try to figure out the bug based on the incoming data. So Kafka can be quite useful, a useful component to have over here. One thing I would change in this pipeline would be SQLite. I use a DuckDB file for my DuckLake, then I attach the DuckLake, which is implemented using SQLite. SQLite does not support concurrency. It supports multiple connections, but once you are writing or I believe reading as well, the table will be locked, and so the query won't fail, but you will have to wait your turn to be able to read or write. Also, once you are connected to DuckDB, if you are using a file for this, DuckDB only allows one connection, so you won't be able to connect to your data lake using the same file. What you can do is just create another DuckDB instance in memory or another file if you need, disk supported computations, and you will be able to, do this concurrently. But I would replace SQLite with Postgres for sure, even for a small project, because you even if it's only you'll want to have processes that are writing to the DuckLake or reading from the DuckLake, and it makes sense to use something like Postgres rather than just SQLite. SQLite is great, but it's better for testing. Even if you are starting from scratch, if you are already running separate storage, if it's all in disk, use SQLite by all means. But if you are already deploying something like MinIO, also deploy just a Postgres instance and you'll be set for everything that you might need to do in the future. So one thing we weren't doing on DataLab before was implementing some kind of orchestration system. So we would need to document every step of the workflow, the command line workflow that we were implementing. And so this way, this serves as a single entry point that is self-documented. So if you are going to use you can just run this command and with -l, and it will show you every task that is available. Some of them can have parameters as well. So you can call, for instance, you can call this MLOps task as just MLOps, and you'll give it a UUID and some feedback. So you are saying that this inference was 0, you are giving it some feedback. And so for this video, if you'd like to test this out, you can just run MLOps all, and this will call the MLOps ETL stage, which in turn calls the ingest stage, and it also calls the transform stage, and then it will call the MLOps train, which will include all these stages over here. So let's go back to the file, and one thing that we have that is new is the DLCTL ML command. So now we have this, and this is our entry point, to train models or to run inference, start up the services for inference. And so as you can see, there is monitor, server, simulate, which is something that we use to simulate inferences, and train. And this will be called using the Justfile for specific datasets. For instance, for this one, we are going to train 4 models, 2 with logistic regression and 2 others with XGBoost. We are going to use 2 feature sets as well. Hence the 4 models. We are going to use basic TF IDF features, and we are going to use embeddings as well. And so we just call it over here. Once you call ML train, which will be this file over here, this will produce scikit-learn pipelines, and everything will be logged into MLflow. So for instance, this train text classifier will load our data set, and this MLflow start run will initialize a new run under the experiment name schema. So this will match our lakehouse schema. The run name will be the method value and the features used. So something like logreg tf-idf. We'll log the method over here as a tag. This is metadata. We'll log it here separately, as well as the features, the number of folds that we are using. We are using 3 folds for this example. The scoring function that we use, so we use F1, as well as the hyperparameter grid that we use during hyperparameter tuning. And we also log the data sets, and this does not store the data set within MLflow, it just stores metadata about our data set, so the size of the data, the number of columns and rows, and as well as the fields that it has, so the expected input and output for our models. And we can also log some dataset tags over here, which for now we are logging, transforming into regular tags. So if you go into the start run, where you just start a run, you don't need any context, with MLflow start run, you don't need that here. Just call it this top level, it's easier to manage. As you can see, we are setting tags, and we are intersecting or appending these tags from dataset into the regular tags as well. And we are logging inputs, which tells us when we are going to serve the model using MLflow model serve, if you like. Not the ideal way, but you can do it that way. We'll expect this format as input. And we also have an MLflow end run where we log the model signature, and we log the requirements for this model, and we are just reading this from our PyProject. We log the model itself, so this is the serialized version of the model that we can use, and this is the only real large file that we are logging within our run. We log the best parameters, and we also log a bunch of metrics that include the best F1 and accuracy for the cross-validation, as well as for the test set. And then we end the run, and this will, if nothing fails, this will produce the green check mark that you can see over here. So in here you'll find the experiment name with the same name as the schema, and in here you'll see the green check marks for all the runs that ran successfully. You've got the metadata I was talking about the training and test sets over here, and you use that model by accessing the artifacts that were logged over here. So if you check artifacts, you'll find that your model has been pickled in here, and so you can request this pickle to MLflow, and you can use it either via an API that you create, let's say Fast API, or even using MLflow model serve, which is also an option, but usually creates really large environments. So if you run build Docker out of this, I was trying it for this model, and the resulting image was over 25 gigabytes, just because I was using Torch in my experiments, and so I ended up logging that into requirements over here. And once you use Torch, you'll also, and Torch is large, you also get a bunch of dependencies from NVIDIA and CUDA, so the image completely blows up. So if you want to use that, you'll have to take care of which dependencies you actually need for the specific model. In my case, I just added everything, but you shouldn't do that in production. And in fact, in production, you most likely will be creating your own services, because MLflow only provides a way to serve a single model, and you might want to have an API where you can serve multiple models. So it might make sense to implement your own. Let's also take a quick look at at the data that we are working with. So we are working with the depression detection dataset from Hugging Face, and this comes with a clean text, an isDepression variable. There is an integer, I believe, and that's pretty much it. We generate an example ID from row number. We rename clean text as input, and we cast this as a double. And then we have a way in here to compute our train test split. We are using 20% for this, for our test set. And we also compute the fold ID for 3 folds, 5 folds and 10 folds. This way, if your data scientists want to use one of these splits, it's already available. We also provide a nisTest boolean that splits the data set into train or test. And this is the training set, where the isTest will be false for everything, and then we'll have the test set in here, where you won't have fold IDs, because this is just for testing. And then we'll provide wrapping methods over here on our lakehouse to help us load this data. So for instance, if we'd like to load the training sets, you can provide it the k-folds that you want, 3, 5 or 10, which are the supported ones, and then it will just provide to you a fold ID column with the one that you picked, and it does not return isTest as well. This is the training set, so where not isTest will always be true. And we have another one for the test set, and another one that is generic for any data set that we might want to load. It always should follow this structure: example ID, input and target. This is quite general for any machine learning problem that you might have, because your input can be text, or it can be a JSON serialized array of features or something like that. So this kind of abstracts it and lets you store everything neatly on your lakehouse. We also use a monitoring data set, which is used just to simulate user requests, so that we can test out the monitor statistics. And this is, different text, and it provides as well a label, so that we can estimate performance on this. So once our models are trained, we can serve inference. We've got this ML inference library where we handle prediction over here. Then we have our server, and our server, besides a bunch of utility requests, we've got our inference request, a post request, as well as a patch request. Post request will run prediction based on our inference request. This will be a post of a JSON including a list of models that we want to use, and if it's a list, it will be randomly selected out of this list. So if we send 2 models, you'll be doing A/B testing. If you send 1 model, you'll be just doing regular prediction over that model, and you can even do A/B and testing with multiple models. and you send the data that we want. So it can be a string or a sequence of float currently. In fact, it can only be a string because we only implemented support for text, and we decide whether we want to log this to the lakehouse. This defaults to true. We might be testing stuff and not want to log it, so we might set it to false in that regard. And so we'll run the inference, and if we are meant to log to the lakehouse, then we will send this to Kafka, to the producer. We'll send this result. This will be queued, as I said before, and eventually written to the lakehouse. This produces a UUID, so inside predict you'll find this string UUID4. This generates a unique identifier for this particular inference, and this is what enables us to later provide feedback on this inference. So in here, this will already be stored into the lakehouse with a given UUID, and once the user gets it back, the user will be able to do another request with that same UUID and some inference feedback. This inference feedback is just UUID and a float with a feedback 1 or 0, some kind of correction. It can even be some kind of intermediate score. We have a slider or something like that. It really depends on how you want to implement this in the UI later. And so the way we model this is as a fast API application, and we take advantage of the lifespan callback to initialize our producers and consumers for Kafka as well. But of course, in a real world scenario, these will run separately within their own containers. This is just, because this is a lab and we want to test that out, but we have Kafka running single threaded, so there is no distributed system, not single threaded, but there is no distributed system. So we also just create a thread over here. In fact, it's just using the sync API for Python, so it even runs on the same thread. This is more than enough for us to be able to understand how this pipeline works. After the yield, these are the destruction instructions. So once the application starts, it will run everything until the yield, and once it terminates, it will run this over here. So it will stop all of our consumers and producers. So once we've got our predictions, we will want to monitor this in production. Since we don't have a production system yet, or ever, because this is a lab, as I was saying, we can just use another dataset to simulate user feedback. So we can look at the data, and now you can just run just lakehouse, and it will connect to your DuckLake. It will check if you have the init SQL generated and generated if it needs it. So use just lakehouse whenever you need. And so now we have, because the data from users will be private, we are using an encrypted storage for a secure stage catalog this time. So we've got our inference results over here. It will look something like this. There are several other fields, but you get the drift. So let's even run it for everything, because there is some feedback already over here from a simulation. Make sure that you keep the date, because you'll need to monitor this over time. So the date is very important. The date when the inference was run, so when it was created. And so besides, and this is encrypted on min.io. course, it's the key is stored within the catalog itself. So as long as you keep your catalog secure, even if the data gets compromised on your storage, it will be safe because it is encrypted. But don't let your database get compromised, the one that you are using SQLite or Postgres for your catalog information. So the way that we are generating this information is via our monitor dataset, and our monitor dataset is just a bunch of text with a label classifying the text as depression or not. It's pretty much the same as our dataset. Okay, it's just that our dataset has got all this extra information, but it is very important that these datasets are completely disjoint. If they are slightly different, if the text is slightly differently formatted, it's also good because you are testing a different case. And what we do is use this monitor dataset to simulate a real-world scenario for users providing feedback, asking for inferences, and providing feedback. And particularly what we do is under the synthetic package, we got this simulate inference, which takes a schema, the number of passes, so we'll do this multiple times, and the sample fraction. So let's say we want to use 30% of our monitor dataset. So if we have 3 passes, it will select 30% of the dataset 3 times, then we'll have a feedback fraction. How many examples of that sample do you want to provide feedback for? So it will select a random number between these two. And out of those, we'll provide some wrong values. So if it's depression, some of them will be, the feedback will provide not depression, just to simulate disagreement between users that provide feedback on the same text. That sometimes happens. It's something you have to deal with in real life. And then we generate a date within this range. So we are simulating inferences between date, min date, and max date. We'll use this decision threshold, usually 0.5 for everything that we did here. And then we'll get a list of models that we can pick from, so our A/B testing. And we'll do this in batches of 100. And this is just so that we can write to our lakehouse after we reach that batch size. And once we do that, we can implement our monitoring statistics, and that's what I'm going to talk about next. And so for our monitoring statistics, we look at prediction drift, also called concept drift, feature drift, also called data drift, estimated performance, and user evaluation based on the feedback. And so there are several ways to implement this, but the way we chose to do it is as follows. So for prediction drift, we use the Kolmogorov-Smirnov test, and we look at this statistic. The higher this statistic, the higher the drift. So this will tell us that our prediction scores distribution will be very different from our test set than it is for, and we do this in weekly windows, for instance. So this week our prediction scores have this distribution, and during the training set, for the training set, the prediction scores had that distribution. How similar are they? And we compute that similarity with using the D statistic. The higher the D statistic, the more drift you have. Now for feature drift, we do this, we have 2 ways identified over here. We do it for the whole data set. So what we do is we always have a reference data set. In this case, the reference features and the current features. The reference will always refer to the training set. In this case, it will be the features for our original training set. And the current will always refer to, in our case, to a weekly window. So the features for instances predicted during a given week. And so what we do in order to understand whether there is feature drift or not is we take a very simple classifier. We use a logistic regression, for instance, and we assign label 0 to the reference data and label 1 to the current data. Keep in mind these labels are not your original labels. So now we are trying to distinguish between our the features for our training set and the features for our weekly inferences. So if we are able to train a model that is able to segment these two data sets, it means they are different. And so this is why we compute ROC AUC. For ROC AUC approximately about 0.5, this is no better than random. If this is the case, then there is no drift, because the model cannot distinguish between the reference data and the current data. But if AUC is above 0.5, this means there is major drift. If it's below 0.5, then you have other problems as well, and you've got major drift, but other problems as well. And so for estimated performance, we do something like confidence-based performance estimation. This is used in some toolkits. I believe Nani ML uses this. I tried to use Nani ML over here, but it was not compatible with the packages that I'm running. So I ended up doing something manually. And the way this works is you essentially just train a model, let's say isotonic regression model. I mean, this is not optional. This is how you do it. You train an isotonic regression model, and you will do it over the models that you want to test. It can be logistic regression or XGBoost, and you'll have a prediction probability, and you will want to this will be your input feature on your isotonic regression model, and your output feature will be whether the prediction label is correct or not. So this will be 1 if the predicted label is correct, or 0 if it's not. And you train this isotonic regression model based on your original training data, and then you use this model with the new predicted probability to predict whether that prediction is correct or not. And then based on this, you can just compute the usual metrics, and you can compute true positives, true negatives, false positives, false negatives. And this is how we computed F1. You can also compute accuracy. And finally, based on user evaluation or user feedback, we just compute a probability based on multiple feedback. So we have a list of 0 and 1s for this particular model. We'll compute, in this case we are using the average to compute an approximate probability of this being true or false, so we have an approximate score based on user feedback, and this can be used to compute a Breyer score, which is similar to the mean squared error, but for probabilities. So it compares the label 1 or 0, an integer, with the feedback, which is a real number between 0 and 1. And so if you get error, if you get lower Breyer scores, this means that if you get 0, it's a perfect calibration. If you get 1, it's your worst possible calibration or outcome. So this means that based on user feedback, your model, if it's near 0, it's performing quite well. Something else that we do not do here is rule-based basic data quality checks, like is it all zeros? Are we getting all zeros from the predictions? Are there any missing values or in the data or something in the features, something like that. Something that should also be a part of MLOps is explainability. So SHAP and Lime are two ways to go about this. We do not cover it here, but I've done this in the past and it can be quite useful. And so now let's take a look at the results from these monitoring scores after we ran a simulation. We decided to run our A/B testing to compare our logistic regression with TF-IDF features and our XGBoost with embeddings. This is our best model, and this is not our second best model, but we decided that, you know, testing this with a different feature set as well would be an interesting first A/B test, and we could do different A/B tests if this model keeps winning with the XGBoost with the TF-IDF or logistic regression with embeddings. And so these are the numbers of inferences that we simulated over time. It's not that many because it takes a while. This is not fully optimized or anything, but it is enough to understand the concepts. And so we can look at prediction drift over here. And for prediction drift, keep in mind that the higher this statistic is, which is what you are seeing here on the y-axis, then the more drift there is. And as you can see, for TF-IDF there is consistently high drift, and this is mostly because our original text our original corpus didn't contain a wide enough vocabulary. So some of our newer examples are producing no values for those features, so most of them are 0, and so there is not enough information to predict, and this ends up being quite, you know, stable. So if you find something like this, you'll get suspicious and you will inevitably need to further inspect. So this is already useful as it is, just because of this. And as you can see, XGBoost has a lower prediction drift, which is positive. For feature drift, we want to know whether our data that we are using for prediction is changing too much or not. So ideally we'll want, this is ROC AUC, so we'll want values around 0.5, so within this line over here. And as you can see, the data is quite different than the input data, so there would be concern in a real world scenario that this would be concerning, and we would need to revise our model. And this happens for both models. As you can see, TF-IDF is much more sensitive to this because it will just disregard those words that it never saw, while for embeddings it is trained on a wider vocabulary, so it can usually handle you know, a more diverse vocabulary. Finally, for performance, for estimated performance, the models from our predictions seem to be performing quite well still, but we know this as well, and this is why we need all these metrics. So this coincides with what we computed during training, where we were getting F1 scores over 0.95, but we know other information. We have this other information that tells us that our models are not quite there yet, right? So finally, based on user feedback, keep in mind that the lower the mean Brier score is, the better. And as you can see over here, XGBoost with embeddings is usually the winner, so there is less error in general over here, although there are some instances where error is quite high. And you know, going back to this, there is high feature drift, there is somewhat high prediction drift, And so that alone is enough to justify why these are so high. And this was just a testing set to demonstrate how this pipeline works, because in real life, if you're not doing AI with LLMs, which is not really, it really depends on the problem, but it's, if you try to classify stuff with LLMs, you'll be quite sad with the end result, let me tell you. XGBoost usually works quite well for classification, and this is the algorithm that is often used to win competitions on Kaggle. And so most of the time the engineers will be working on features, on feature engineering, on extracting features, and this is the most gain you can get is from data engineering, so cleaning up your data quite well, normalizing everything, and then doing feature engineering, extracting several features. And yes, it's 2025 and this is still completely relevant. Not everything is solvable by an LLM, and keep that in mind, and always be critical of whether you can solve your problem with an LLM or if there is some other better strategy. And usually if you decide to not go with an LLM because it's not adequate for your problem, then you'll probably also spend less money implementing your solution, because this usually ends up being quite cheaper. XGBoost, I believe only recently on version 3 did they add GPU support, so XGBoost can work quite well with CPU only for prediction. So you don't even need to pay for a VM with a GPU, which is much cheaper. So always keep that in mind when you are doing business and working seriously on your machine learning problems. Next time we'll go into DevOps land, showing how to use Terraform with a shared state. We'll be setting up Proxmox CTs and VMs to create a DataLab infrastructure that you can use in your home lab or for small in-house data projects. Over time, we'll also release videos showing how to manage a DuckLake instance on that same infrastructure and how to deploy models using a custom Docker image that can communicate with your data lakehouse. These videos will not be released in sequence, so I'll keep a playlist with all MLOps end-to-end relevant videos. As usual, you'll be able to find the companion blog post for this video at datalabtechtv.com. You can follow the channel on Blue Sky or join Discord to discuss all data-related topics, from data engineering to DevOps or even software engineering for data products. I'm recently looking into Go and creating some stuff with Go, so let's discuss. If you like the video, don't forget to drop a like and subscribe for all things data.